Well, this is the end of the computational complexity theory learning material. Therefore, I would like to summarize what this material was about. Let's see how much wiser did we get, hopefully. Recall how we started in the beginning. We dealt with well-known computing problems, primarily the search problem and the sorting problem. We analyzed the complexity of a couple of well-known algorithms for the above two problems. Then, based on that analysis, we compared those algorithms with each other. Then we started to explore the theory with the main objective of defining large complexity classes, for example, NL, L, P, MP, X time P space, and so on. Let me not to repeat how any of those complexity classes is defined. We have already acquainted with that knowledge, right? Well, we then drew a map of those complexity classes and located well-known common problems on it. To do this, we needed some useful tools. For example, such a tool is the witness theorem, which is very handy for proving a language to be in NP. We got to know the tool of reductions, which is necessary for proving a problem to be complete for a complexity class. Furthermore, if we have already found complete problems, then we are able to use well-known algorithms for other problems by reducing them to the complete ones. Thus, reductions are very powerful tools. In my first video, I envisioned that you are gonna be a programmer one day. Now, at the end, I am envisioning that you are gonna be a very conscious programmer. When getting a new programming problem, you will be able to investigate if, first of all, the programming problem is decidable. That is, will your program always terminate in finitely many steps under any circumstances? This is a highly important question that should be answered already at the beginning. If it turns out that the problem is decidable, then you will be able to investigate if the problem is tractable. That is, it can be solved in reasonable time. And furthermore, you will possibly have an idea even about its space complexity. How will you usually do those investigations? Well, by reductions. Try to reduce the programming problem to an already known algorithmic problem, to a graph problem, to a numerical problem. It depends on the programming problem you are facing to. Try to construct such a reduction even in your mind or on a sheet of paper. If you have showed that your programming problem can be reduced to a well-known problem, then you gain a very strong tool, algorithms. Algorithms for solving that well-known problem. Classic algorithms which have been available for decades or centuries. Those are typically optimized algorithms. So the message here is that you should develop programs not in a hasty way. You should not hack in a brute force way, despite temptation, of course. You should wisely try to reduce your programming problem to already existing, well-optimized algorithms. So I think after done with the computational complexity theory learning material, you will be able to work as a very conscious programmer in the future. A programmer who can examine programming problems and can rely on already existing algorithms and hence can develop prototypes in a very rapid way. Hence, the success is more probable since you will be able to develop faster and more efficient algorithms. And what is even more important, you will be able to recognize sooner if your programming task is hopeless. Yeah, so, well, let me and the creators of this learning material wish you success in your future and not too optimistic career in software development. Just do the best you can, that's all.